This CI run built a temporary Android version of our downloadable game assets and uploaded almost 500 megabytes to Cloudflare R2, the online storage behind those downloads. Then, Unity cleared the cached download files for this test and tried to load every asset on a list we prepared before the build. All 989 of them. All 989 loaded. Every cross-check passed. Green. Our old validator also said green. That script inspected the source files and addressables setup saved in the Unity project. 989 registered entries in 48 groups. Validation, okay. But when we deliberately broke the project in 6 different ways, that old validator still said green. So this episode is not really about adding more CI. It is about one annoying question. When CI says green, which part of the asset's journey did it actually check? To answer that, we need to follow one asset through every place where the system can quietly lose it. Take the hallway background on screen. Before a player can download it, that one image has to survive several handoffs. First, code and backend data say that this room needs a background. The project must contain the image and its Unity meta file. That meta file contains a stable identifier called a GUID that lets Unity recognize the same asset even if the file moves. Next, Addressables gives the image the name the game will request. It can also attach labels, tags used to load a whole set at once. Each asset belongs to an Addressables group, and that group's settings decide whether the image is included and delivered remotely. During the build, Unity packs many assets into larger bundle files. It also creates a catalog, an index that maps each runtime name to the bundle and download location containing it. CI uploads that catalog and those bundles. Finally, CI clears any cached bundle this image could use and asks Unity to load the image by the name we expected. Something can go wrong at each step while everything before it still looks correct. The backend can request an image that was never created. A healthy source file can be left out of the build. A valid catalog can point at an older release, so every download succeeds while we test the wrong content. Most importantly, we cannot ask the catalog what should be in the catalog. We need a packing list created before the catalog exists, and then we compare the two. Before trying to break the pipeline, we asked whether we had accidentally built several checks that all did the same job. We had not. Each check watches a different step. First, we compare the files the game says it needs with the files that actually exist in the project. That is, the required file check. If a room needs a background image and that image is missing, this check catches it. Unity cannot inspect or register a file that was never created. Second, for every file that does exist, we ask whether Unity registered it under the name the game will request. That is, the Unity registration check. If an image exists under the wrong Addressables name, the required file check passes, but the Unity registration check catches the wrong name. Third, our full-body character images contain transparent space around the artwork. To space several characters evenly in a room, we generate a small layout file that records the visible width and center of each character. It also stores a fingerprint of the image those measurements came from. The layout freshness check compares that fingerprint with the current image. If we replace the artwork without regenerating its measurements, the file and registration checks pass, but the layout freshness check catches the old data before the character is positioned incorrectly. Finally, we inspect where each Addressables group is configured to load from. That is, the group settings check. A remote asset can have the correct file and Addressables name, while its group is configured to load from the installed game instead. The earlier checks pass, but the group settings check catches the wrong delivery setting. These checks were not redundant. Each one caught a different mistake, and we had already made versions of all 4 in the real project. Our mistake was treating green answers about 4 individual steps as proof that the entire delivery chain was healthy. Once we knew why each check existed, we tried to break the checks themselves. To test the old checks themselves, we built a disposable miniature Addressables project. We called it the Failure Lab. A script copies in the old validation tools, breaks one rule at a time, records whether each break is caught, and deletes the project afterward. We ran 29 controlled cases. In 23, clean input passed or the intended mistake was caught. In the other 6, a broken project still reported green. One of those false greens came from a missing label. A label is just a tag on an addressable. Our game uses one tag to preload all the assets belonging to a character. If one asset loses that tag, asking for it directly by name can still work, but the character preload quietly leaves it behind. The old validator checked the asset's identity, group, and runtime name, but never checked the tag. Another test disabled the Unity setting that tells addressables to include a whole group in the build. The source file remained. The saved addressables entry remained. The validator remained green. But Unity could leave the whole group out of the catalog. We also had a download test that asked the built catalog for all of its addresses and then loaded every answer it received. That sounds complete, but it has a matching blind spot. If C is missing, the catalog returns A, B, and D. The test loads 3 addresses, reports 3 successes and 0 failures, and never learns that C was supposed to exist. That was the key mistake. We were asking the catalog to define what complete meant. To know that C is missing, the expected list has to come from somewhere other than the catalog itself. We did not need a bigger counter. We needed our own packing list. A catalog cannot be its own checklist, so the first CI stage creates the checklist before Unity builds anything. In the code, we call that checklist the expected manifest. The manifest is not a handwritten list of 989 addresses. We generate it from 3 sources. The first is the set of asset names our code is allowed to request. The second is the ID selected by the backend for this run. The third is the inventory of source files and Unity meta files that actually exist in the project. Some names are fixed in code, such as the menu texture. Those fixed names live once in a shared C# definition. Unity and a faster .NET checker that runs without opening Unity both read that definition, and we generate the TypeScript version from it. We do not maintain 3 copies by hand. Other names depend on today's game data, character IDs, room IDs, and emotions. The first CI stage asks the backend for them once and saves the response. Every later job uses that frozen answer, even if the live backend changes while CI is running. The general naming rules can then become an exact list of files this build should contain. A small number of assets deliberately ship inside the app through Unity's resources system instead of being downloaded through addressables. They use a separate loading helper, so the code must choose the system explicitly rather than falling into one by accident. We also scan the game code to enforce one doorway into asset loading. Code cannot bypass our loader. Type a complete addressable's name by hand or invent a different rule for assembling that name. Values that only exist while the game is running, such as the current room ID, can still be passed into the approved helper. Each manifest row now connects one runtime name to one source file and one Unity identity. It records the asset type, its group and labels, digital fingerprints of both the file and its metafile, and which backend rule, if any, requested it. Some assets remain managed even when the current demo does not request them, so they stay checked without pretending they are active. The complete manifest gets its own fingerprint, so every later job can prove it received the same checklist. Unity then compares the real imported project with that manifest. Does each row point to the same file, Unity identity, runtime name, group, and exact set of labels? Is every group included and configured for remote delivery? Do the settings controlling how its bundles are compressed, reused from cache, and checked for corruption match the approved policy? Any disagreement stops the build. These relatively cheap checks form Gate 1, the first blocking stage. If they fail, CI never starts the expensive Unity builds. In the clean run, 49 contract tests passed. The resulting list had 989 addressables entries in 48 groups. 678 were requested by today's demo configuration. The other 311 were not needed by the demo today, but we still check their Unity registration so they cannot silently drift. The same rules are used at 3 different moments for 3 different jobs. First, a small piece of editor automation runs whenever an asset is added or moved. It immediately assigns the expected runtime name, labels, and remote group settings. Its job is to prevent common configuration mistakes while we work. Second, developers have a setup command that repairs the whole project on demand. It removes old labels, removes cases where the same managed asset was registered twice, and makes the project match the manifest. Run it a second time, and nothing should change because the project is already repaired. Third, CI-only checks. It never quietly repairs the build it is judging. If it did, a green result could hide settings that were never fixed and committed. When the committed project does not match the manifest, CI stops. Try to prevent the mistake while we work, provide a repair button when the settings get out of sync, and make CI refuse anything still broken. One shared set of rules, 3 different jobs. Even perfectly configured Unity settings do not prove that the same release reached the online storage players download from. We need to test the uploaded files before publishing them, but we do not want a deliberately broken experiment anywhere near a real release. So every run uploads to its own quarantine folder in R2. Its path starts with _CI. Nothing points players at that folder, and the workflow does not tag it as a release. The catalog itself contains the URLs players would use after publication. In a catalog built for Android Release 17, every bundle URL must still name Release 17 and the Android platform. If we rewrote those URLs to the quarantine folder, we would no longer be testing whether the catalog names the intended release. CI solves that in 2 steps. First, it checks that every URL names the expected release number and platform. Then, only for the download test, it redirects the network request to the matching bundle in quarantine. The catalog keeps its real identity, while Unity still downloads the exact bytes we just uploaded. The first attack changes the URLs written inside the catalog so they name the quarantine folder. Those bundles exist, so a simple download can still pass. But the catalog now describes the wrong release. The release identity check catches that mismatch before Unity loads anything. The second attack approves one catalog, records its digital fingerprint, and then changes the catalog before upload. The changed file may still be valid, but it is not the file we approved. Comparing the expected fingerprint with the served one catches the substitution. In the logs, that fingerprint is called a digest. In these experiments, a green workflow means the trap worked. The deliberately broken step failed, and the expected error appeared in its evidence. If the bad release passes, or the expected error is missing, the experiment is red. Successfully downloading something is not enough. It has to be the release and the catalog we actually approved. A catalog is only the map. The bundles are the files containing the actual asset data. The next 2 attacks keep the map correct and damage one bundle before uploading the temporary release to quarantine. One attack removes the bundle completely. The other cuts the file down to a few bytes and uploads that corrupted copy. Both changes affect only this disposable Android build. Before loading anything, the test asks Unity to clear cached bundles for every expected asset. Otherwise, a good copy left on the test machine from yesterday could hide a missing or damaged file today, giving us another false green. The test again loads every name from the packing list created before the build, not whatever names the catalog happens to report. An asset stored in the damaged bundle must now fail to load. Short timeouts and a limited number of retries make that failure predictable instead of letting a broken download hang CI indefinitely. Every fault test folder also contains a marker file saying it is unsafe. The publishing script refuses to copy any folder carrying that marker, so even if someone later makes a mistake in the workflow conditions, the publishing tool itself still rejects the sabotaged build. One run may build the same asset release for several platforms. That creates another possible false screen. Android passes, publication starts, and only afterward do we discover that a selected Mac OS or Windows build failed. We prevent that by making every selected platform finish the whole checklist, match the manifest, build the expected files, upload the approved catalog and bundles, and load the remote assets from quarantine. Only after all selected platforms pass can CI copy them into permanent release folders. The clean run from the start of the episode selected Android only, so Android is all that particular run proves. The workflow can coordinate the other platforms, but we will not claim evidence we did not collect. That run also used verification-only mode. It stopped after proving the quarantined Android build, without copying it into a permanent release, making a Git commit, or creating a Git tag. Real publishing is not one magic all-or-nothing switch. Our two copies platforms one at a time. The workflow commits the updated Addressables project files and creates a Git tag afterward. A separate backend setting decides which release players receive, and this workflow does not change that setting. That separation between copying files and selecting a release for players is important. A failure halfway through copying could leave an incomplete permanent folder that needs cleanup, but it would not direct players to that folder. The quarantine uploads also still need an automatic expiration or cleanup job. We began with 6 ways to break the old pipeline while every check stayed green. The old lab still reproduces all 6 false screens. We kept it as the before picture instead of quietly changing the old test until the embarrassing result disappeared. Now the pipeline creates its checklist from code rules, one frozen backend response, and the source files in the project. Unity checks that its real settings match that checklist. After the build, CI confirms that the catalog and bundles contain what we expected. After upload, it confirms that the approved catalog arrived, still names the intended release, and can load every expected asset with an empty cache. Every platform selected for the run has to complete that whole trip before final copying can begin. This is absolutely paranoid. We tried to remove every check we could not justify. Unfortunately, they all had receipts. But there is an honest end to the proof. Suppose a human puts the wrong valid portrait in the expected source location before we create the manifest, and then approves that new manifest. The pipeline can faithfully build, upload, and load the wrong picture. CI does not understand the character, the joke, or the artwork. CI can prove that the source file we approved kept the expected Unity identity and runtime name, entered the intended build, and loaded from the uploaded release. It cannot tell us whether we approved the right picture.